Hi everyone. Hi, good morning. A very good morning to all teacher. Okay. Before we start, I actually want to explain with all teachers. So before that, is it my voice clear for all teachers? If clear, please let me know. If not clear, also please let me know. Clear? Okay. Thank you so much. I am not the one who will teach all the teachers because the trainer will in soon. So maybe while waiting for the other teacher to enter our Zoom webinar, first of all, I would like to tell that this is actually Zoom webinar where is auto turn off your voice and also turn off your video. So don't worry. Okay, so if you guys have, if all the teachers have a question, please put in the Q&A symbol. I believe that below here, I think everyone will have Q&A symbol. And also, if you have any question, you can directly to all panelists. Okay, so before we start, maybe I would like to show one video about Penang Science Cluster, what we do while waiting for the other teacher and also our trainer. So I believe that most of science and also physics teacher do not know who is PSC, what PSC do, but most of the teacher that know about PSC is ASK Asal Science Computer teacher and also Reka Bentuk and Technology teacher. So let me introduce, share my screen. Okay, may I know who cannot see the video other than one teachers? Everyone can see the previous video that I show about Penang Science Cluster. Yes, no problem. Okay. Maybe the teachers that cannot see my video, yes, we have a video about the Penang Science Cluster, but it's okay because I will maybe explain what we actually doing after this. Okay, so let's wait around 4 more minutes for our trainer to come in. He will come in soon.
Hello, Amira. Hello again.
Hi, Mr. Pham. Okay,
Hi.
you already here?
See you again.
I can see you. Wait a minute.
Nice background.
Yeah. Okay, so right now we already have 40 teachers.
Oh, okay.
Yeah, 40 teachers. Yeah. So okay, so I think maybe we would like to start first, especially for the introduction part before we start our teacher training. Okay.
Yeah, sure. Go ahead.
So hi, good morning to all teachers. So today, thank you for joining our virtual oscilloscope teacher training. So I hope that all the teachers will gain something today from us. So, okay, I introduce myself. I am Amira from Penang Science Cluster. I also would like to introduce my friend, Diana. Diana, maybe you can say hi to all the teachers because next week she will coordinate this program.
Hello, I'm Diana.
Hello.
Okay, so I also would like to introduce our trainer for today, Mr. Fook, a former director of engineering. So previously he worked with Motorola in R&D department. So now he also really active in volunteering in Penang Science Cluster. So for today, he also volunteered us to teach all the teachers about the oscilloscope. So I hope that all the teachers will get the benefit from this class. Okay, before I introduce a bit about Penang Science Cluster, a few things that all the teachers need to know. First of all, please keep your phone in silent mode. I hope all the teachers can focus during the class, only for 2 hours, okay? And second thing is, if all the teachers have any question, you can send via the Q&A or you can put in the chat, okay? Third thing is a really important, okay? So I need all the teacher to take 2 photos during the training, and all the teachers need to upload the photo in the Google form at the end of the session, okay? At the end of the session, I will display 2 QR code, one for LDP and the other one for the JPNPP report purpose. So please be aware about this thing, okay? So next thing, okay, so make sure all the teachers prepare this thing before we begin our class. Make sure you have a strong internet, your own laptop, pen, and also a netbook. Okay, before we start, I would like all the teachers to go to this website first because we will learn about Desmos calculator soon. Okay, maybe the teachers can take a photo first, or Diana, you can share with all the teachers. Please open this website first. Okay, next thing is about the Google Classroom. So this Google Classroom is for the exercise for all teachers for today training. So please go to the Google Classroom first right now. So this is the class code. So Diana will share with you the Google Classroom class code. Okay. Until now, all the teachers clear? Or I am too fast? Is it all the instruction clear? If clear, let me know so that I can proceed to another slide. Okay, all right, good. Okay, so next thing, okay, so learning outcome for this week and next week, okay? So for your information, all the teachers are compulsory to join our class for this week and also the next week. So for today, the teacher will learn about the Desmos calculator, and for the next week, the teacher will learn about the multi-sim application, and all the exercise for the teacher will be in the Google Classroom, and please complete it. Don't worry because we have 1 week. Please complete it so that Mr. Farm know your problem, and also for all the teachers to practicing these new tools. I believe that all these tools can be used during your PDPC. Okay, so let me introduce a little bit about the Penang Science Cluster. So Penang Science Cluster is a non-profit organization where our aim is to spark interest, spread a culture of innovation and entrepreneurship in STEM among the students. So what do we offer to school? Okay, so what we do offer to school, okay, we have a science kit to school where this is actually related to biology, physics, science, and also chemistry. So we have a sensor that we can provide for the school, and we also provide the teacher training and learning to school in Pinang. So actually all our programs are free. The teachers no need to pay or anything. Just how to contact, I will tell you later. Okay, next, code on wheels. Okay, this is code on wheels. Maybe few teachers have see our car before. We come to school, we bring 40 laptops, and also we teach the student hands-on activity with the Arduino and also Python. The next thing, we also have a curriculum activity where we have a tech mentor astronomy. We also have a tech mentor robotics. So Mr. Fook volunteer teach the student in the radio telescope. So he teach about the crystal radios. What we do inside here is actually the student need to build their own simple radio. Correct me if I'm wrong, Mr. Pham.
Yeah, that's correct. Yeah, it was very fun.
Yeah. Okay, so we also have a Project Ignite. So Project Ignite is one of our annual program. Just this year, we don't have a chance because of MCO. So this is a program where all the students come to our places, come to Penang Science Cluster, and they need to build their own prototyping. They will learn Arduino, they will learn microbit. Okay, so next thing, Penang International Science Fair. If all the teachers have heard about the Penang International Science Fair before, so last year we done this PISF in PISA, so we do a lot of workshop. So Penang Science Cluster is one of the one who organized this event. Okay, so just this year, we already cancelled our PISF for 2020. We don't know how about the next year. We hope that this COVID-19 will end soon. Okay, so actually all our program are free and approved by JPN Pulau Pinang. So, and our program are focused on student and teacher. How to join our program? So all the teachers can contact me directly. Maybe can ask me what kind of program that we are offer. Maybe I will introduce a bit, because right now during MCO, we actually have an activity. We actually have a lot of free activity online because we cannot do the physical teaching, but we still provide we work with JPN and we provide the teacher training, but it still depends on what kind of teacher training that we will teach. So yeah, I guess I'm that things. Yeah. So that all from me. So after this, we will start with our learning session. So before I end, I would like to ask all the teachers, do you have any question? If you have a problem with Google Classroom, let us know so that Miss Diana will have, can help you. No, all right. Okay, so if no, I think I will pass to Mr. Pham so that we will start our teacher training right now.
Okay. Yeah, thank you, Amira, for the introduction. Good morning, everybody. It's very nice for you to spend your time here. Thank you for spending your precious time with us. And today, I just want to give you some basic training on oscilloscope. But before that, maybe let me introduce myself. Yeah, let me share my screen here under the screen number 1. Okay, I hope you see my PowerPoint slide over here. Okay, if you cannot see, just wave your hand or put a message, I cannot see or I cannot hear. So basically, this is my bio. My name is Mr. Pham. It's quite a unique name. It's F-A-M. So I think you cannot forget this name. I am currently a freelance trainer. Prior to that, I was with Motorola for 30 plus years, and was with Inti for a short while. And you can actually reach out to me using this email for any questions related to this training session. I graduated from University Malaya back in 1984, a long time ago. Number of awards during my career in Motorola. 3 patents and 2 publications. So if you want to know more about myself, you can Google my full name. You Google my full name and you have some more information about myself. My interest is basically in the area of, one of my interests is basically in the area of education. And I volunteer myself with the Penang Science Cluster. And the, oh, somebody cannot see the PowerPoint slide. Everybody can see the PowerPoint slide or just one person?
Cannot.
Cannot see it, right?
The teacher have a problem that cannot see the PowerPoint.
Oh, okay, okay. So, but everybody else can see the slide, yeah?
Teacher, maybe you can try first. Okay, everybody can see.
Okay, sure. All right, let me continue, yeah? So I contribute my time volunteering with Penang Science Cluster. And okay, this is some background. So this is my one of the early photos back in 1984 in Motorola then. So at that time, no computer, no handphone, no internet. It was quite free at the time. But we have a lot of paperwork over here. So there was life at that time. And back then, we used a lot of equipment. At the back of this desk here, let me see whether I can get the annotation up. Okay, the annotation. Okay, I found the annotation. Okay, over here you can see this is the oscilloscope. Okay, it's a very old technology scope, but it was very useful at that time. So there are a lot of changes in the oscilloscope now. So I will just brief you on what are the changes and how to identify those. Okay, I cannot get rid of it, annotation. Okay, you excuse me for
You can remove the drawing.
Yeah, because I'm quite new to this control. Yeah. Where is the
Click at the notation.
Annotation. Remove.
Yeah, remove the drawing.
Clear all drawing. Okay, all right, okay, thank you. So it's a bit clumsy for this one.
No
So
worries.
I volunteer myself with the Penang Science Cluster back in 2017. So it's already a few years. So I'm working with the radio telescope project, basically to build a radio telescope over here to monitor the activity in the sky or the space. Yeah? So yeah, and back in 2019, we went to various schools to build up this crystal radio. We call this project Crystal Radio. Basically, the student build up this board here. Okay, let me show the annotation again. Annotate. Draw. Okay, so this is the crystal radio, which the student will do soldering and build up and test for themselves. And we went to various schools here, like 4 or 5 schools. And some of the schools have oscilloscope, but they're not sure how to use it. Some schools don't have, and some schools want to buy some oscilloscope. So for this training, I'll just give you a guidance of how, if you want to buy an oscilloscope, what are the things to look for, so that you know you will not know how you're going to apply the your training or your class using oscilloscope. Okay, that's some information about myself. Any questions so far? Not, I'll go to the proper training. Okay, let me clear the annotation again here. All right, okay. So we'll start with the proper training. So this training, the purpose of this training, well, because of the MCO, we were not able to conduct a face-to-face training, and avoiding the distancing criteria. So the best thing that we can do is do online training on the oscilloscope using available software and tools that is available on the internet, so that you can have a feel of how an oscilloscope works before you actually touch an oscilloscope. So this is the introductory topic on the oscilloscope, and this will probably take less than 2 hours. Okay, so probably about 1.5 hours. So if there's any question, we can fill up the time. If not, then we can end this class early. So the content of this training for the whole duration, basically an introduction of the oscilloscope. Let me get the annotation here. Annotation. Okay, so we're going to do an introduction of the oscilloscope and some signal basics. We learn about signals with the help of this tool called Desmos calculator, which is a free online software. You don't have to log in, don't have to download. It's available online. You can actually use it for various calculations. I will give you a demo of how to use it. It's very useful. If you have not used it before, you can try. If you have used it, I think you have seen the many features in this calculator. Thirdly, we'll do the waveform, how we're going to analyze waveform. And we have another tool here called Multisim Live. But this application need you to log in or to register yourself with this website. Later, I'm going to show you. And the software is free for you to actually try it out and learn. And we're going to have a live demo with the one of the oscilloscope that is available in the Penang Science Cluster. We'll just show you some features and some functions on the scope, so that you know, because the scope is very complicated. We have a lot of buttons, and a lot of knobs. So introduction will give you a feel of which knob is for what function, so that you understand, where to look for if you want to do some changes to the waveform. So for today, we will cover item 1 and 2. And for the following week, we will finish off with item 3 and 4. Okay? Clear the annotation. Clear. Right, so how are we going to learn this training? What are the learning modes? We have theory and demo. Theory is not very sufficient, not a very good learning way, but the demo is a very good, effective way to learn about any topic. Tutorials and exercise, of course, these are helpful. And of course, the assessment is important so that we can get feedback whether the information is helpful to you or whether some information are missing or not sufficient. So the total learning hours is about 8 hours, 50% on the theory and demo. We're going to spread it out in 2 sessions, and we're going to have exercise and hands-on for 4 hours. So it's a balance, 50-50. So 50% on the theory and 50% on hands-on. So the tools are available online, and of course, we need to go to the Google Classroom. You can actually download the copy of this presentation in a booklet form for you to print out or for you to view on your computer. So go to the Google Classroom, you get the soft copy of the booklet, and from there you can actually follow the program on your own. So the basic requirement for this class is that you need a basic laptop. You need a standard internet, because these tools are online all the time. Your internet has to be online continually all the time. All right, so let me just go straight into this introduction here. Right, we're going to cover what is the purpose of this scope here, why we need the scope, and what type of scopes are available, so that you understand what to get for your classroom or your school. And some of the basic features that you need to be aware before you buy a digital scope. and what are the application or frequency ranges that you need to be aware, okay, before you buy a scope. You may be overbuying a scope, or you may be underbuying a scope. So you've got to choose the right scope for the right application. Yeah. So what is the oscilloscope? Basically, the word oscillo, let me get a annotation here. So the annotation here is a Greek or Latin, I'm not very sure. So it's oscillo is anything that is oscillating. Scope is the meant for to describe an instrument for viewing, maybe a telescope or microscope or a periscope. So anything with the scope is meant for viewing or for display. So the oscilloscope here is a very useful tool, especially in the engineering and science and physics, because by itself, electrons cannot be seen. So we need to see electrons, or we see the effect of electrons before we can actually analyze and debug problems. So the oscilloscope is very helpful because it converts the electrical signals into a visible trace on a screen like this, so that we can actually view what is happening on maybe a board, or maybe on the equipment, or maybe on some electrical traces. Yeah. So the basic display for the scope, it displays the voltage, always display the voltage, most of the time on voltage on the y-axis, and the time on the x-axis. Okay, this is the most often the display. Of course, you can display current and another trace also, but the most common display is the voltage and the time. It's used to do testing, verify circuits, debugging, troubleshooting electronic components, especially in the industry area. Almost all the industry use the scope. Let me clear the annotation. Right, so the scope here is used in various places. For example, in the factory test environment, we have this setup here. Let me get the notation again. Okay, so this is the we call this test station or a test rack. So this rack is actually in the factory or industry area, and in this test rack, you will have an oscilloscope in one of the rack, so that the test, the unit under test, the signal will be channeled to this scope here for analysis and testing. So it's used also for troubleshooting. For, let's say, the board come out, it didn't work well, so the technician need to troubleshoot and analyze. So the scope is a very instrumental tool to use in the industry. Also for field repairs, because if the scope, this is a very handy scope to use. It is portable. It's like a multimeter which you can carry, and it's battery powered. And the field means that the outdoor, that means the base station, that is, we don't have any power socket available nearby. So this portable oscilloscope is very handy for you to actually analyze in the field itself. Of course, it's used a lot in the research lab and in education too. You can see the students here. We have a lot of exercises based on the oscilloscope. Okay, let me go to the next one. Oh, there's so many drawings here. Okay, let's see. Annotate, clear all. Okay, so in the you have to be aware that there are two types of scopes here. First one is the analog scope. Let me get the annotation here. Okay, this is the analog scope here. You can identify this because it is pretty long. All right. So this scope here is the length is very long, because inside here there is a cathode ray tube. So cathode ray tube is a long tube that is in this scope here. That's why the length is very long. Okay. Unlike the new one, this is the new one. This is called the digital scope. The digital scope is very slim, which is the 13.3 cm only. So the digital scope, the depth is because we don't have the CRT or the cathode ray tube anymore in this scope here. This is very slim. Okay, and also it can show you different colors like green color or yellow color. Rather than this old scope is only choosing one color, which is green. And we go to next slide. Oh, I need to clear the annotation every time. Okay.
Yes.
All right. Okay. So you can see the trace when you turn on the scope here. You will see that the let me put the annotation here again. Okay, so you say old scope, the trace is a singular color. It's like a cathode ray tube. Okay, the new scope, the digital scope here, you can actually have multiple colors like yellow or green or blue or red on the trace here. So this is the digital oscilloscope. So if you want to buy or thinking of buying a scope, please don't buy this. This is a very old technology. Okay. So buy the new technology with the digital scope, which is have much more features compared to the old one. Okay, unless you keep old things, then this will be a good equipment to use because it's getting very rare for this one. Okay, let me clear annotation again. Clear annotation. All right, so this is the overview of the digital storage scope. The short form for this one is called DSO. This is the digital scope, and it's a storage scope. It's just like your handphone. It has storage, so it has like a memory that you can actually capture information and store inside the scope and keep it for you to review and analyze. Let me get the annotation back again. Okay, so this is the digital storage scope here. It captures the input signal and convert it into a digital waveform or digital form, which is the 1 and 0. And it stores into the information for analysis. You can recall it, you can zoom into the information, and you can actually analyze the information or the waveform. And you also can actually, the data or the digital form can be put into like a pen drive. You can actually save this picture or save this waveform by using a pen drive into this USB port here. Then you can actually move your information to a computer to show in your classroom. So on the display, you will actually display the waveform, okay, and also it will measure the information for you. You can measure the like frequency, basic information like frequency, the voltage or the period, and on the scope itself. So in the scope is quite powerful because it has some algorithm that can help you to analyze and measure and give you the information without you doing the calculation and conversion. So this scope is very useful to getting results quite quickly. Let me clear this annotation. Okay, let me move on to the next slide. Okay, so how to read this digital scope? First of all, you look at the label over here. The first thing you need to see is this DSO. When you see a DSO, means it's a digital and it's a storage and it's a scope. On the other side here, you will see this is the frequency. So you need to know what is the frequency of your application before you get the scope. So a scope can be very expensive or can be affordable depending on what is the frequency or the coverage of the application that you intend to look for. And the other information to look for is this giga sample per second. SA is a sample per second. So this is like how much memory or how much information you want to store into the scope, or how fast the information you want. Okay, I have another slide to show you how to read this performance or the description here. All right, so when you buy a scope, it's just like you buy a computer or buy a handphone. You need to understand the features and also some performance factors. Like, for example, the first one is you need to understand how many channels you want to use your scope for. So there are this connected here. These are the number of scope probes or the signals that can go into the signal at the same time. So you can choose whether you want a 4-channel scope or a 2-channel scope or a 4-channel scope. So depending on what you want to analyze. So in this case here, the number of channels means that will impact your budget. So a 2-channel will be quite minimum. A 4 channels you need to spend more money on 4 channels. And the bandwidth is important because the ranges, it tell you the range of the application you're trying to analyze. For, let's say, a simple application like radio frequency, maybe a megahertz range will be sufficient. But let's say you want to analyze like a computer board, which is running very fast. So you probably need a very fast bandwidth or high bandwidth, okay, or higher speed, okay, for the scope to handle. This figure that the sampling rate, I'll tell you more about the sampling rate. This is the memory depth, okay, and the mode of the scope. You need to understand. If you want to look for is the thing that you need to look for is the triggering. If you see a scope without any triggering, you should not buy it, because the triggering is a very important feature in any oscilloscope. A scope without triggering is not worth buying. And also some of the scopes, they will do some measurement for you, like frequency, time, period, etc. Okay, and some of the scopes depend on what you want to do. You can actually have a USB port over in front here, okay, for you to import or export your waveform from this oscilloscope. And some scopes also have the Ethernet connection at the back of the scope. I'll show you later. And also HDMI connection for you to actually show the waveform, okay, in your classroom using a projector. So this is the newer form of the display. The VGA is the older form of the display interface or projector. So this scope can connect directly to a projector for you to show your students of the waveform. Let me go to next slide. Yeah.
We have a question. What
Yeah.
is maybe you
What
can
is triggering? Yeah. Okay. So I will show you more information later. This is just the beginning. Yeah. So you just remember the word triggering for a while. In the demo and exercise, we will tell you more about triggering. Okay. Just hold on your question for a while. Then I'll come to your point later. All right. Okay. So at the back of this scope here, we have this USB. Back and front, you have USB connection for you to do some software interface with the computer. And we have this Ethernet port, LAN port. Okay, this port is very useful in case, let's say you want to control this oscilloscope remotely. Like for example, if let's say your scope is in the school and you are at home, so you can actually control the oscilloscope from your home, okay, using a IP address of the oscilloscope, and you can actually capture waveform and do some measurements in the school while you are at home. So this is very useful for you to work remotely. So some of the engineers, they have a lot of measurements done in the company or the industry or in their lab. So they can go home first. And when they go back home, they just open up their computer, and in the laptop, they will see the activity of the measurement going on the scope and communicated back to the computer. So if they want to do some changes on the measurement, they can actually instruct the command from their computer and trigger a different measurement from to the scope. So this is very useful for remote control of the oscilloscope. So these are the VGA port for you to display to the projector. And let's say that this is a secure lock in case you want to leave it on the bench and you don't want people to take it from your bench and then get missing. So you have a secure lock there. You can tie this to the lock, and then the other side you just tie it to the table so that it won't get stolen. All right, so now there are a lot of features in the scope that we need to learn, but I'll give you an analogy of what are those features in relation to your camera and your phone. So a scope is a very, not many people use scope in their career or in their school, but a lot of you, in fact, all of you probably have a camera. So I'll just use this as an analogy of how you can relate some of the features of a scope to a camera. So you can imagine that the number of channels on the scopes is like the number of channels on your phone camera. So like the iPhone 11 Pro, you got 4 cameras. So that is a lot of cameras. So depending on what you want to do, you can live with 1 camera or you must have 4 cameras. So these are the number of channels. And the bandwidth is like what are application that you want to use for your camera. So most of us use the camera to take pictures, okay, and videos. So this is the normal application. But some of the cameras, we can actually use it for infrared capture, okay. Like for example, you want to use it as the temperature, like to see the temperature of your forehead, to see the temperature of a hot equipment or something that electrically hot. We will use infrared, or you can actually use this as the body heat sensor. So this is the application. And there's some camera that actually can see ultraviolet images. So this ultraviolet light is not visible to our eyes, but for some application, they have an ultraviolet camera that can see ultraviolet light to analyze some of their research. So sampling rate is like a frame rate. Okay, normally our camera is 30 frames per second. So when you take a video, it is running like 30 frames per second. So this is normal. Some of us have like a slow-mo mode in the camera. So a slow-mo mode, you need a faster frame per second. So 60 frames per second. So when you go into slow mode, you can actually capture like a sports event, and you can actually slow-mo it, and then you can see the effect of the running more dramatically. So this is the frames per second, 60 frames per second. And let's say that you want to capture the, let's say, an arrow or a bullet going through, let's say, a watermelon or any object, you need a faster frame per second. So if you want to capture this type of like video, you need at least 1,000 frames per second for you to capture that event of that very fast moving bullet. So the sampling rate is similar to a frame rate. So a faster sampling rate means you can capture more information, very quick information for your display. So this is some analogy. Memory depth is like similar to like an image resolution. Okay, so the more memory depth you have, the better resolution you can see the waveform. Okay, so some of our cameras, maybe we have 12 megapixel, may or may not be sufficient for some of us. Some phones are now coming out with 50 megapixels, may or may not be enough for some of us. And the latest phones, I think they have 108 megapixels for their image and basically pictures. So basically, the higher your image resolution, you're able to, once you capture the image, you can zoom into your picture and you can see more details. Okay, so in the same way, the memory depth of the scope also, if you have a lot of memory depth, you can actually capture the image of the waveform and you can zoom in and you can see a lot of information in the details. So the higher the depth of this scope, the better you will be able to see the image. Some of the modes, okay, like triggering modes. Imagine that, let's say that you want to take a picture with your handphone. When you want, okay, sometimes you want to take like a selfie image of yourself and your friends. So what you do is you set a timer. So the timer could be a 2 second or a 5 second. The minute you set a 2 second or 5 seconds, when the countdown is up, then the camera will take a photo. So this is like triggering. So when you press the button on the camera for you to take a picture, you will count down 5 seconds or 2 seconds. So this is like a triggering for the camera for you to take a picture. So in the same way, the scope also have a triggering. So triggering is very important for a scope because you want to capture certain events at the right timing. Okay, so imagine your camera, if you don't have a timer, you press the picture with your finger, but your finger, let's say, shake. You have then your picture quality won't be so good. So in the same way, you set the timer 2 seconds, and then when you press 2 seconds, you stabilize your hand. After that, the picture can be captured in a steady. So some of the cameras, you have face detection. Okay, the minute, let's say, the camera detect that their face, okay, and they're smiling, okay, then they will take a picture. So this is the trigger, a trigger for the camera to do something. Okay, so some of the cameras have voice trigger. The minute you say capture or shoot or whatever, the camera will recognize this voice and you will start taking picture. So in this case here, triggering is like a signal or some condition that will trigger an event for you to capture. So at the scope here, there may be some critical pulses or some critical waveform that you want to trigger, but it happens at a particular time. So we need to actually set a certain trigger so that it can capture the information at the right time. So this is some information about triggering. We'll learn more about triggering, okay, in the next class. So like the I/O interface, you have like a USB on the bottom of your phone, and you have audio, you have Bluetooth and Wi-Fi. These are the interface to your other devices from your phone. Okay, in the same way also, the scope itself need to interface with the computer, need to interface with the projector, need to interface with the USB cable to another device, etc. Okay, so this is some analogy. It's not a really direct explanation, but I think it's quite useful information for us. If you don't have the scope for you to try out, this camera will be a very good analogy to assess the performance of the scope, or how you're going to read the information. All right, so now this is the, when you buy a scope, it comes with accessories. A scope without accessories is no use, okay? Because the accessories are the one, like for example, this is the, and I have the scope probe here with me. This is the scope probe. Okay, it has the connection to the equipment itself, and this part here is the one that goes to your circuit board. So the minute if you have a circuit board, you can actually probe that signal anywhere using this scope probe. So without the scope probe, the scope is not much use. In addition to the scope probe, you would have like a ground clip. You need to have a ground clip. The ground clip is important for you because without a ground clip, the signal will not be captured accurately. So one portion of the ground clip will be attached to the ground, and another one will be attached to a signal for you to analyze. Yeah. So another useful accessory is this grabber. We call this grabber because you can plug into this. So this is the tip here, and it presents a hook for you. You can see. Let's see. I'm not sure. You can actually clip and grab a circuit board wire, for example. Okay, so this is very useful for you to have hands free. You can actually grab into a pin here, and your hands can be free to manipulate the scope for you to do the right setting. Okay. The next thing that you need to see is the tuner. We have the tuner. It's like a screwdriver where you can actually do tuning and calibration on this scope probe itself. So this tuner is like a screwdriver, and you can insert into this certain screw here that you can actually adjust. You can adjust the waveform. If it's not calibrated, this tuner or the screw here can adjust the waveform until it is nicely. I'll give you a demo later of what the use of this tuning. So when you buy the scope here, make sure you get the accessories. You don't get the accessories, then you need to buy the accessories. Let's say you have a 2-channel scope, make sure you have 2 sets of this accessory. You got 4 channel, make sure you got 4 sets of this accessory. So it's important for you to use it for probing. All right, so now, just now we saw about DSO. DSO stands for Digital Storage Scope. There's another type of scope called MSO. What's the difference? MSO is short form for Mixed Signal Oscilloscope. So Mixed Oscilloscope have an additional port here. Let me show you the annotation. Yeah, at the bottom of the scope, there is a extension, a port here that you can actually plug in many extensions for you to analyze more signal. Okay, I will show you the next picture to help you to understand. So under here, okay, just hold on your question for a while on the mixed signal oscilloscope. So it analyzes actually both analog signals and digital signal. So analog signals is like the waveforms like this. Digital signals are actually basically 1 and 0s that basically digital boards and computer boards exhibit digital signal. So this scope here, you can actually display both analog signals and digital signals at the same time. So this is very useful for those engineers who does like digital board and also analog signal evaluation. For this one, the MSO, in addition to the 4 channels, you have the 4 channels that go into that you use your scope probe to put the signals in the scope. The MSO have this digital probe that you can go into this port here. You can extend the number of probes from 4 to 8 probes or 16 probes or 16 channel, we call this. So let me go to the next slide to show you. All right, so before that, how you read the MSO. So the minute you see MSO means that it is a mixed signal oscilloscope. That means that this oscilloscope is going to be expensive because it has a better performance and also more features compared to the DSO. Okay, so the frequency of application and also the sampling rate. The higher your sampling rate, you can see the image better or better resolution for the scope. All right, so this is how you connect the scope. Let me remove the annotation here. Clear annotation. So this is the scope, and you use the extension over here with the extended probe that are like grabbers. These are grabbers that you can actually put onto a digital board, and the signals will be channeled to this scope here, and the information of 1 and 0s and the digital signals will be actually displayed on the scope itself. So you can have up to 16 traces or 16 channels of digital signals and up to 4 channels of analog signal. So this is a high performance scope. If you really need this, then you need to get a MSO. It's called Mixed Signal Oscilloscope. Okay, let me go to the next slide here. Okay, so there are other forms of oscilloscope also you can find in the market. For example, this one, this is called USB oscilloscope. Basically, You don't see a display. Your display is actually on the computer, and the control is also on the computer itself. So in this case here, the scope is this box here. This is the oscilloscope box, and this is the scope probe, and this is the digital extension for your cable. So this is considered like MSO. Okay. So this oscilloscope, so-called oscilloscope, connect to a USB cable that goes to your computer, and you will display the waveform on the computer. You have an application running on the computer that interface with this hardware for you to capture the information on the scope and also on this extension. So the thing is that you need to install a software for you to work with this hardware. And for performance, high performance feature, this box is also not cheap. So basically, this is very handy and very portable. So you don't have to carry a big oscilloscope with you every time. So you just use a very small box, and the display will be your computer. Since everybody has a computer and a display, this could be quite a good solution for you to be portable. And another one is this handheld portable, which I showed you just now. Is useful for those people who work in the field or the base station that don't have the power plug available easily. And this is very handy for you to carry in your pocket. Clear. All right, so there are many type of brands that you can buy from. A lot of them are from China, and there are some that are from US, like Keysight is from US. This is from UK. Regal, I think, is from Taiwan. Rhodes and Sword is from Germany. So there are many choices for you to select, depending on your budget and also your preference and your branding preference or your school preference. It varies. The cost varies. So the cost is the structure is. Let me show you how it costs. And cost. A minute here. Okay, so this is the cost structure here. So if you click the link that I showed just now, you can see the range of the pricing. So this is the lowest end for the Keysight oscilloscope. Well, you need about 2,000 ringgit to start off. Okay, and the higher end one is like 72,000 ringgit. So the range is very wide. So depending on the application, you can go for 2,000 ringgit or 72,000 ringgit. So, but if you approach like companies like Keysight or Rhodes and Sword or those companies that I've shown you just now, they have discounts for like for the purpose of education. They have like a discount. You can give them a call. Let's say you intend to buy, give them a call and say that you're from the school and from the education sector. They would maybe give you some discounts that you can enjoy. All right. So beware of the pricing if you want to buy an oscilloscope. Beware of the pricing that you need to pay. Okay. So we're going to go to the next topic. Anybody got? We'll just pause here. If anybody got any question so far. All right. Good. So we'll look into the signal basic because the oscilloscope captures signals, but we need to understand what is a signal before we can actually capture it and analyze it. So this topic here will give you an introduction of what are the signals. So we're going to go through some mathematics a little bit, some basic wave equation, some demo. I'll give you a demo using the graphic tool, and some waveforms that are useful in terms of the communication, wireless communication, and some waveforms that are non-sine wave. What are they used for and what are they? So to understand some basic equation or some basic example, I've used this water ripples. If you actually throw a stone, okay, in a pond or swimming pool, you can see that there will be water that will come up from the source of the when the stone land into the water, and the water will actually ripple out of the pool. So this is, I think everybody observed this and is familiar with it. And over here, you can see that as you drop the stone on the water will be disturbed, and it will actually form crests and valleys up and down. And at the same time, the wave will also move outwards. Okay, let me show you the notation. Okay, so as you drop the stone on the pool, the water waves, or the water will be disturbed, and then some of the waves will come up, some will form valleys, and some will form crests. At the same time, the waveform will also travel away from the where the stone went into the water. Okay, so this is the alternating waveform that moves like a wave or an alternating waveform over the distance. This is traveling out. At the same time, if you monitor at one point over here, this point here will go up or go down depending on how the waves come up. So this is this waveform is like we call this the sinusoidal wave. So it's like a sine wave. So this is the natural wave that is occurring very naturally in the environment. In many examples. Let me show you the next example here. Clear all drawing. All right. So this is the simulation from a website called PHET. So it is a physics education and technology website. Basically, it is a lot of tools here. You can actually go to get animation for you to explain to your class better. So instead of talking for hours, animation will actually save a lot of time, and also you understand better. So in this case here, you go to this website called PHET, and all right, let me show you. Okay, so this is the animation that is ready for you. So what you do is you can actually click on this button here, and you can turn on. Let me run it this time. Okay, so you can click on this button. A water drop will drop, and then you can see the waves coming out from the middle or the center of this drop, and then it will go out. Okay, the dark areas are the valleys. The bright areas are like the crest, the up, and the dark valley, the dark one are the crest. So if you can actually turn the picture sideways, you got the side view, right? So you can see from the side view, the waves are created from this water droplet, and it goes out, okay, to the end of the whatever tank or pool. At the same time, it also moves up and down at a certain position. So in this website, it provides you some tools, this is like they show you a tape, a tape. Okay, you can actually pause this animation. You just pause it, and then you can use this tape here. And from here, you can actually pull this tape to illustrate that this from this point here to this point, it is called a period. The period of the wave, the wavelength. The wavelength of this wave is 2.7 cm. Okay, so the wavelength of this wave is defined by one point here to the next point where it repeat itself. You can actually take up a scope here also. There is a scope that you can actually take one of the scope probe, okay, and put it say at this point here. Okay, let's remove this tape for a while, and when you animate this app, you can see that the at a fixed point, the wave actually go up and down. Okay, so this is a sine wave. So from this animation application is very helpful to actually illustrate the wave, how the waves are generated. Yeah? So you can take away this probes here, and you can play around. Like for example, you can actually increase the frequency. You can increase the frequency of the drop. Okay, you can see that the wavelength gets shorter and shorter. This is the if you reduce the frequency, you can see that the wavelength get longer. Wavelength get longer, wavelength get shorter, because frequency increase, then the wavelength will be shorter. You can also increase the amplitude to make it more impactful, or you can actually reduce it to make into like a smoother wave. You can slow it down, or you can do normal. You go and try it out. It's very useful, and you know, it will help you to explain to your students about waves and about the concept about wavelength, and about also the period. Okay, so this is very useful. Try it out, and then you see the results, and then let me know how it goes. Okay, so this is the demonstration that I showed you just now. So you can see that the wave travel over the distance, and at a certain spot, the waves will go up and down at over time. So some of the properties of this wave are like wavelength. So just now when we pull the tape, the measuring tape, from one point to the same point where it repeats itself, okay, this is called the wavelength. Okay? And this is over the length, and this is the time. In this waveform also, from one point to another point where it repeats itself, we call this time period. So this is the cycle or period or cycle. So this will repeat itself continually. And we also define the frequency as 1 over period. This is the time, and 1 over the period is defined as the frequency. And another term that is very useful is the speed, the velocity, or the how fast the wave travel is defined by the wavelength, one wavelength divided by the period. So in short form, velocity is the frequency multiplied by the wavelength. So this is some minimum mathematics here. So the question is, how fast does a wave move? So in the example just now, the water waves travel roughly about 0.3 meters per second. Okay, this is relatively slow compared to, let's say, sound waves. A sound wave travels about 300 meters per second. So radio waves or light waves travel at 3 times 10 to the power 8, okay, meter per second, which is very fast. So different waves travel at a different speed here. And from our experience in lightning and thunder, the minute you see the lightning, okay, you start to count. Okay, if you can count, let's say, if you see the lightning and you hear the thunder 10 seconds later, then you can calculate, you know, that this is approximately instant. So you can actually calculate if 10 seconds, your storm or your thunderstorm is probably about 3 kilometers away. So you see the next lightning and the thunder comes maybe 2 seconds, that means the thunderstorm is coming to your house or your area. So by listening to the waves, you can actually determine, you know, whether to close your window or to get ready for a heavy thunderstorm. So the relationship with the wave and frequency I have illustrated just now. V, the velocity, equals to frequency over the wavelength. This is a very common equation that is used in the engineering, especially in communication engineers or in communication engineering. All right, so what are the application and different frequency and many waveform, many wavelength? So this is the frequency spectrum. A spectrum is a range of frequencies. In the radio, your radio, FM radio, they are operating about 100 megahertz. So this is 1 megahertz, this is the 10, and this is the 100 megahertz range. Okay, let me keep notation. Okay, so this is the about 100 megahertz range. This is where your radio would operate. Okay, and your handphone are currently running about 1 gigahertz or two, in between 1 gigahertz to 2 gigahertz. So your microwave oven is running about 2.4 gigahertz, around the same frequency as, it's about the same frequency as the Wi-Fi also. And for body scanning, let's say you go to airport in US, you got body scanners, they are probably running in the range before the terahertz. It's 1 terahertz. And your remote control, like your TV remote control, they are operating in infrared. This light is not visible, but this light is waves is emitted from this remote control. Okay, so don't look directly into the remote control because it actually have a strong light coming from this control, but you cannot see. So that could be dangerous. So this spectrum here, this narrow spectrum here is what you can see with your eye. It's very narrow compared to the whole spectrum of the frequency. And some application like ultraviolet, they are used like for wafer fabrication, for their screening, or before they actually do the mask of the IC, they actually have the fabrication mask over it, and they shine the ultraviolet light over it to actually make sure some areas are etched and some areas are not etched. And of course, for you go to the dentist or you go to the hospital, they give you an X-ray to check what's wrong, with some of your parts inside your body or your teeth. And gamma rays are available, or actually a lot of them in the outer space. And some people ask, are these waves dangerous? Okay, so these waves, the guideline is that anything above the ultraviolet, this you have to be careful. Okay, with the if the strength is you don't control the magnitude or the strength of the X-ray, you get into trouble, because and also gamma rays, because the frequency is very high in eta hertz and zeta hertz. The wavelength is very, very short. Okay, the wavelength is very short and it has a very strong impact on your body. You will actually, we call this, you will ionizers, or actually they can knock off some electrons from your molecule, and there will be some like form of change of the body structures. If there's too much of exposure of this X-ray, and especially gamma rays. And of course, you have seen like movies in the cinema, like X-Men or Marvel or whatever, So, but the thing is, how they get into the mutant condition is, basically they have overexposure of X-ray, and that's how they became mutants. Okay, and anything below this frequency we consider safe. Right? If there's an increase in the strength of this frequency, the effect that you will feel is like you'll be hot. Right? For example, microwave. If it's too much exposure to microwave, you forget, or you have microwaves cooking inside your oven here. The worst case is that you get burned or you get heated up. But for X-ray and gamma ray, your molecule change. Okay, then there's a mutation. All right, so this is some guideline. Of course, you hear of people having like cancer, you have too much of ultraviolet. So this is like the borderline case over here. Okay, so much for this one. Let me go to the next. So this is the, you may be asking, how are waves generated? So there are many types of waves. There's the sound waves. There's the light wave. The sound waves is generated from anything that waves are generated by anything that is vibrating, okay, or anything that is oscillating. Like for example, sound waves. You can actually use an instrument, musical instrument, piano or guitar, and you plug in one of the string here, then the waves will be generated. Okay. In the same way, also light waves like LED, when the electron jump from one band to another band, it loses its energy, and in the same way, it gives out its energy in the light form. Okay, so this is, let's say, it could be a red light, and when you jump from one higher band to another band, it will generate a blue light. So this, and as long as it keep on moving up and down, you will continue to generate a light waves. So the key thing is it has to be vibrating. Okay, the guitar has to be vibrating. The electron has to be going up and down this valence band to create these light waves. In the same way, electromagnetic wave, EM waves or electromagnetic wave is the electrical signal that goes into a structure like an antenna. It oscillates up and down through a wire antenna. You will generate an electric field, and the electric field around you will generate a magnetic field. So in this case here, the EM waves will actually propagate from the antenna, and this is very useful for wireless communication. And most of the electrical board that you use on your maybe application or your devices or equipment always have a crystal oscillator. Inside the crystal oscillator, there is like a piezoelectric material that actually when you apply electrical energy, this will vibrate, okay, very quickly, and that will generate electrical signals in the sine form. All right. So this is, let me give you a demo of this virtual. There's the virtual oscilloscope that is online. You can use it to try it out. Let me show you, where is it? Here you go, the virtual oscilloscope. So you can see that as I speak, the waveform changes. So let's say if I change it to sine wave, a sine wave will appear, and you can actually change your frequency also, a higher frequency or lower frequency. You can change it, and also you can change how big the how much signal, how big the signal you want to see on the scope, or you can reduce it. And also you can change your time span. You want to see maybe more waveform, you just put into longer time, and you want to see less waveform, you put into shorter time. Okay, you also can change your scale to be larger or smaller. All right, so let me at this time maybe demonstrate to you a sound coming out from a guitar. All right, so let me have my come over here to show you a guitar. There you go. This is a mini guitar. This is not the full-size guitar. This is the mini guitar. So in this guitar here, if I plug in one string, for example, you can see the waveform. Okay, you can see the waveform here. You can actually stop the waveform. Okay, you can see the waveform here. If I can freeze it, you can see the waveform here. So I can plug many strings and different frequency can come out. Yeah. Alright, but actually sound itself, the wave itself, you play the note itself, it is not interesting. It is not pleasing to your ear. So normally for a guitar or musical instrument, we have a combination of waves. A combination of waves will be more pleasing to our ear. For example, if I play this chord here, this is a C chord. Sounds better right now. Okay, it sounds better versus one of the wire here. Okay, so it's not very. So this is a C chord, and this is a G chord, and this is a A chord, and this is the D chord. Okay, so maybe since Merdeka or Malaysia Day is coming, let us well, voluntarily, if you want to sing along with me, maybe Amira can sing louder. My voice not so good. I sing like frog. All right. So over here, a combination of strings produce a melody. All right. So a wave itself is very boring. So you need a series. You need a series of waves, then you can make your listening pleasure. So a series of waves, a combination of waves is more pleasing to your ear. Okay, Amira, get ready to sing. Puji dan syukur kepada Ilahi, anugerahnya tiada terhingga, kedamaian kemakmuran Malaysia ku bahagia. Merdeka untuk berjaya, kebangkitan dan kami junjung cita-cita kepada negeri. Okay, I stop here lah, and I convert this to a music class already. Yeah, all right. So basically, you can use your virtual scope here to see the waveform, right? And you can see at certain frequency what is the waveform, and then you can view it for yourself how it looks like. Yeah? Right, nice voice. Oh, thank you very much. Actually, I sing like frog. I also miss out the tune. All right, thank you very much for the compliment. I'm very happy now. All right, okay, so now we go to the next one. This is the illustration of the sine wave. So sine wave is naturally occurring. And if you actually have an experiment using a spring, right, you let it move naturally. If you monitor the movement over time, it is generating a sine wave. So we can call this function a sine function. The y is a function of time, and a is the amplitude, and it's a sine wave. Okay, so we call this a sine wave or a sinusoidal waveform. All right, so to illustrate further, if you have a let's say a ball, okay, or let's say okay, imagine, since this is an astronomy mentor class, so you imagine that the sun is in the middle and the earth is rotating around the sun, okay, and you monitor the x or the y axis, you monitor you will go up and go down, and you follow the trace over here. Okay, if you monitor this as the angle, as you move the angle, you will plot the amplitude versus the angle in this sine waveform. So to simplify the mathematics, this angle here, theta, is also can be written as omega t. Okay, omega is actually 2 pi ft. So f is the frequency and t is the time. I won't go into the derivation. I think you can go into your textbook to see. And for this sine waveform, so this is the function time, and this is the r, is the amplitude, okay, from the center. It's a sine function, 2 pi frequency and time. All right, so this is the basic wave equation. Y equals function time, a sine 2 pi ft. And this is we are going to use the Desmos to plot this for you, and you see clearly. So this is the basic wave equation. A more general wave equation will be a sine 2 pi ft plus phi. A phi defines the phase. For example, if the phi is a certain number, it will actually, this sine wave will shift left or right, right or left, depending on this phi here. So this is a more general equation for the sine. Later, you see how important it is, phase information. So now high frequency have a lot of use, especially in the radio communication, for wireless communication. Electron EM waves or radio waves travel very far distance. So you actually have a source from one antenna, you can pick up very far away because of the electromagnetic wave property for wireless communication. That's why your handphone and radios, they travel very far distances for you to receive them. So, but waves, if the waves itself and it doesn't do anything, it does not carry information. So for communication wise, you have a signal wave that carry from one point to another point, but if it does not carry information, it is not much use. So what we do is if you want to carry information, we call this modulation. All right. So when we modulate, we would actually carry information into the wave. So like for example, if this is the waveform over here, if this is a waveform notation and notation here, right? So this is the waveform, and if you substitute the amplitude here as either a 0 or 1, then the waveform have some information that you can communicate. Okay, like for example, let me clear this notation. All right, so if you have a is 0 or 1, means that when A is 0, share a notation again. If A is 0, there won't have any signal, no signal. If A is 1, a signal will be transmitted. All right, so by putting a series of no signal and signal, the information can transmit to another source meaningfully. For example, if this is a short pulse and this is a long pulse, a series of short pulses, 3 short pulses, and a series, another followed by 3 long pulses, and followed by 3 short pulses. Okay, it means SOS, you need help. Okay, so this is the Morse code that is used many years ago. So if you have a light, okay, if you're stranded in the middle of the ocean and you have a flashlight in your camera, you just flash 3 short flashes and 3 long flashes and 3 short flashes. Then people who are in the military or in the sea, they recognize this code as SOS. Then they will come to your rescue. So this information is embedded because if there's no modulation on this wave here, it's got no meaning. If you change the waveform, then it has some information that can be transmitted as meaningful information. All right, let me go to the next one. Clear all drawings. All right, so there are 3 ways you can actually send information or modulate the information. So in this waveform, you can actually change your amplitude. Notation again. Okay, you can actually change the amplitude. Okay, and just now you saw in the Morse code, by changing the amplitude 1 or 0, there's some meaningful information. Like you can send SOS, which is it could save your life. You can also modulate the frequency over here. You can have high frequency, low frequency. That is also another form of information. Or you can actually change the phase. That is also another form of modulation. So you change the amplitude, we call this amplitude modulation or AM modulation. You change the frequency, we call this frequency modulation. You change the phase, this will be phase modulation. Okay, so there are only three types of modulation in communication. So these are the few of them. Okay, so the example of modulation can be demonstrated in our speech. For example, if let's say if you open up your mouth, let's say for example, a baby, when the baby cry, you will just have one tone. Okay, let me try to illustrate. A baby cries will be okay, but when the baby cries like this, the mother will say, what is the baby trying to say? Is they're hungry, or is they want attention, or they are hurt, or whatever. But the minute the baby close the mouth, they say, ma, they want mommy. Okay, that is information, right? A tone itself got no meaning, but when you actually modulate it, it has meaningful information. Like for example, in this picture, let me show you the video. Am I? Okay, the video is here. All right, so in the YouTube, you will see this. This is a very good illustration.
Ship, shops, coat, coil, coin, coup, cook.
So you can see that when you make a speech, you use your mouth to open and close. You use some tongue to actually move around your mouth. You use your nasal channel here to generate tone or to manipulate or to change the tone. And your voice box is the one, the source of the tone. The source of the tone without the tongue, without the mouth, without the nasal channel here will not carry information. But when the source of information or the source of the wave come out, the tongue will change the pitch, okay? Change the frequency, or the nasal channel here will change the frequency. The mouth will change the amplitude, or maybe this one will change the phase. Okay, so this is the illustration of information being carried in a wave. So look into the video and you can see it's quite interesting video over here. So in the AM modulation, we can actually see that the if we replace the amplitude here, just now the A factor was here. If we actually replace, this was the A just now, and we replace this A with the AM modulation or amplitude. Sine 2 pi f m t. This m stands for modulation, your voice, the modulating signal, and fc is we call this carrier. This is the higher frequency carrier, and this is the low frequency carrier. So in this equation, describe the amplitude modulation. Okay, don't worry about the equation later. We will have a demonstration. Right, so when you actually go into the Desmos calculator, you will see that the AM modulation is in this form. All right, it's like a lump of waves coming together. So in this AM modulation waveform, the outer one, the one that is being shown in the arrow, show the notation here. The wave that is outside here is the your voice. Okay, yeah. The one that's inside here is a higher frequency voice, high frequency signal. So you have the higher frequency, you have a lower frequency that is controlling the higher frequency, whether it is like a certain amplitude or not. Okay, so this is called AM modulation. And also you can change the frequency modulation by replacing this term here, the 2 pi ft in the previous slide, with this function here, 2 pi fc plus your modulation signal, mf. Okay, don't worry about the equation. I'm just trying to show you so that I can illustrate the concept. Yeah, I'm going to put this equation into the Desmos chart for you to illustrate or to show this modulation. So y equals to a sine 2 pi fct plus your we call this the modulating index. Okay, by increasing or reducing the index, the amount of modulation will change. Sine of your 2 pi f of your modulation plus your phase. Yeah. So this is the frequency modulating by this changes this equation here. Right. So this is how the FM modulation looks like. So when you look at the waveform, sometimes the frequency is higher and sometimes it is lower. Okay, so the frequency is changing. The amplitude remains the same, but the frequency within the wave change. So versus the slide just now, the amplitude changed, but the frequency remained the same. So there are different ways of modulating the frequency. All right. So now we're going to a topic of non-sinusoidal wave. Huh? Everybody okay? Do you need a break or you carry on? Okay, no signal here. I will continue. Okay, so for non-sinusoidal waves, means that it doesn't look like this. It doesn't look like this, but it looks like a square wave, and this is called the triangular wave. Triangular wave, and this is we call this the sawtooth. Okay, if you go to like your workshop at the Penang Science Cluster, you take a saw. This is how it looks like. We call this a sawtooth. Okay, so many other waveform also that are non-sinusoidal. So what are these non-sinusoidal wave and how are these generated? So square wave, for example, okay, this is a more complicated equation here, but don't worry. This is how you describe a square wave. A square wave actually consists of many sine waves combined together. So this is the expression of a square wave. So if you combine, let's say, a sine omega t plus a sine 3 omega t plus this term here, plus this term here, plus this term here, you will get a square, like a square waveform. Okay. So now if you can actually integrate this, you add many terms until you have a lot of this term, you finally get a perfect square. So the key about this is that anything that is non-sinusoidal actually consists of many sinusoidal waves combined together. So actually this also is a sine wave, but it's combined in different combination. So in the same way, a triangular wave, you can actually use this expression and then you see that you'll come out as a triangular wave. The third one also, tortoise, you can actually put in this equation, it will come out in this equation. So the short form for this long equation is this short equation. This is the summation. Summation means that you want to add one term with another term with the next term. If you start with the n is 1, we have this sine 2n omega t over 2n. You put 1 into this expression, you get the first term. You put n is 2, you get the second expression, and so on until you get infinity. You get a nice sawtooth waveform. All right, so basically, is the the rule here is all the period or any waveform, whether it's sine wave or square wave, can be expressed into this equation here, which is a sine waveform and a cosine waveform with a certain coefficient, an or bn changes. Okay, so don't worry about this equation. This is called Fourier series. So the whole principle about this equation is any waveform can be generated using a combination of sine wave. A cosine is also a sine wave. A cosine is a sine wave, but it's phase shifted by 90 degrees. So basically, is any waveform can be generated by a combination and series of waveform. Okay, so any question now? I'm going to do a demo for the Desmos graphic calculator.
Okay, all the teachers have any questions before we go to the Desmos calculator?
Okay.
Okay. You guys take 5 minutes rest.
5 minutes, yeah? All right. Sure. Okay, see you guys later. Make sure we come back. All right, thank you.
So during the 5 minutes, I will share with all the teachers one QR code for editing. Wait, got one teacher raised hand. Do you have any question? If the teacher has question, you can put in the Q&A or in the chat.
Story that I have described just now, I think maybe 5% went into your head. So by using a demo, I think you have a better understanding. Okay, so let me go into this.
Mr. Tom, before we
Yeah,
start, I have one more question. For the
yeah,
next question, if we discuss about how to use oscilloscope, digital or analog?
yeah. We're going to use the digital scope. I don't think PSC got the analog scope anymore. So we are going to use the digital scope, but the buttons are the same function.
So it means they can apply to the analog also?
Yeah, you can. The basic function apply to the analog scope.
Okay.
Okay, so I will use the digital scope to demo. Okay.
Okay.
So if you if you go to the Desmos calculator, you can see like empty graph paper. Everybody see it. Okay. So in this empty graph paper, you can actually type in a certain expression. So how to use this graph is basically on your left hand side, you can type in your equation for you to plot. For example, a basic one will be say y equals to x. Then you plot y equals to x for you. Okay. And you can actually put another form here, plus 1, and then the waveform will go up by 1 step. Okay, or you can actually put here the equation here. You can use this. You can okay, under here. Let me put the annotation. This is the box where you put in your equation for you to plot this graph here. And the other one is the here there's a button that you can click to have more functions. Let me get this out first. Okay. Over here, when you click here, you show the keypad. The keypad here will actually have a certain expression that you can include in your equation. Like in this case here, these are the square function, and this is the B means you can put any function or any power you want. This is the greater than or less than function, square root function. This is the pi symbol you can put here. And these are the, if you don't have a keypad or keyboard, you can type in using the icon here. And over here, these are, you click on the functions over here, you see there are other functions that you can use for your expression. Like you can put in sine wave or cosine wave, or the other functions here. I've already forgot. Cotangent, this is cotangent, this is cosecant. I already forgotten my mathematics. So anyway, these are the sine, hyperbolic sine, cosine, and tangent hyperbolic. These are statistics here. These are distance. Okay, there are many functions that are available. I have not tried all of them, but a lot of people have used many of these functions for their purpose. And other miscellaneous, you can actually put in special symbol like integration or summation or this function here. I'm not very sure. I forgot what function is this. Or dy dx or polygon, etc. There are many functions to explore. But for this case, we will just do the basic one. So keep in mind that you have this on your left hand side, the expression to key in. And if you need help to have a different of like a symbol, you can use the keyboard here. You can open up the keyboard here to have more functions for you. And on your right hand side, you can see the spanner. The spanner is actually where you actually change your setting for your graph. All right, for example, if your x-axis you want to change it, then you can change it to let's say your scale to -5, and then this one is 5. So this changed already. So you can change this also to expression of to range of 5 and to 5. Okay, so you can actually change the step size. You once this step is the how fine you want one box to be. For example, if I want this to be a 1, then one box will be a 1. see how it goes. Huh? Already move out here. So you can zoom in with your mouse. If you place your mouse, you click on the wheel. Huh? The wheel will zoom in and zoom out. Okay, so you can see it clearly. On the spanner, okay, or you can use this to zoom out and zoom in. Or you can use your mouse wheel to actually zoom in or zoom out. Okay, or you zoom too much, you press the home button, I think automatically scale for you. You go to spanner, there are other functions here, but I'll just focus on the function that you will use later. So under this expression, let's say, let me clear this annotation here. Annotate, clear all. So this is the basic line equation. So you can have a certain expression like x. Let's see, x squared, x to power. You put here square, and then you add, and you have a y power square equals, let's say, 4. A circle will be drawn for you. Okay, this is the expression for a circle. All right, so using the Desmos chart, you can actually plot in many various functions you can explore on your own. And this Desmos will be used for help us to understand the wave. Okay, another example, like for example, this one is x power of 2 divide. You have a division here, divide by, let's say, 4. Then you can have add y square, okay, and divide by, let's say, 9, okay, and then you put here equal to 5. So this will be an ellipse. This will be an ellipse form. So you can draw many graphs using this Desmos chart here. So try it out on your own. Go to the tutorial. If not clear about how to use the Desmos chart, you go to the Google Classroom, and the first tutorial will show you a couple of videos to guide you of how to use this Desmos chart. All right. So there are also exercise number 1 for you to familiarize yourself on this Desmos chart. Go ahead and try it out yourself. Let me go to the next exercise or the demo. So if we can, okay, you can actually close this one by putting an X. You X this guy, then the previous expression will be cleared for you. So in this case, we want to do, okay, I forgot to inform you just now on another function. We call this a slider function. Y equals to, let's say, x plus y. Let's say you have a y equals to mx plus c. This is the general equation. So, but the Desmos chart can actually assign this m and the c according to a variable. So, for example, you put an m here, and you put a C as slider, you will see that if I change my C, my graph will respond immediately. So if C is 0, my intercept point will be a 0. If my C is, let's say, 6, my intercept point will be a 6, and so on. This M here is also, you will vary the gradient. This is the gradient of 1. If I change the gradient of 2, the graph will change by itself also, okay, and so on. So negative gradient, this is positive gradient. And also you can animate. You can animate here by a button here. You can animate, and you will animate by itself. And you want to animate it faster, you click the animate speed, and then you can actually speed up the animation very fast for you. Okay, and let's see, back to normal. And also you can actually animate this guy. So you can actually animate both M and the C simultaneously. It will show to you. All right, so this is quite interesting. Let me stop this one. You can stop this guy, and let me clear this expression. So go ahead and try it out yourself, huh? Okay, and do the exercise. This will open up many other, expression that you want to try yourself for your students. So the second demo I'm going to give you to show you is on the sine wave. So you can actually write the expression for a sine. Sine equation will be y equals to a, okay, sine, open bracket, 2 pi. You can actually type pi. You will change to pi, or you can actually use a pi in this expression here. You can use the pi from this expression here. We can put into this formula, and or you can actually type in pi manually. You will come up, and the frequency f and a t. Okay, you close the bracket, and they will ask you want slider for all this expression, and then you will say that I want expression for a, I want expression for f. Okay, so you can see that this is a sine wave already. So I can increase this sine wave to see clearly, and basically this is, you can actually slide the frequency up and down. You can change the frequency, and you can change the amplitude. All right, so this is the some of the features of Desmos chart. Go through the exercise, and then you will understand better. So in this case, if I want to change if let's say the other expression is if I want to put in the phase plus the phase, so the expression for the phase is phi. You just put phi, the expression phi will come up. Okay, so you can add a slider for phi, and the phi. When you change the phi, you can see that the waveform will shift left or right. Okay, so now if let's say for this expression, I have I think a question here. Let me address it later, or let me try to address it later. So from here, you can actually put in the exercise, put in the expression as shown in the exercise, and then after that you see the expression. You follow the exercise and the instruction properly, you will see the waveform coming out in front of your eyes. Okay, so go through the exercise, and after that, you have any problems, you go to the Google Classroom, and we have a chat that you can actually try it out. So now there is the third demo on the show. So the third demo is the non-sine expression. Okay, that's a question of the how you differentiate sine, AC, and DC. Okay, let me if let's say you have this sine expression here, but all the time this sine wave is around the center. This is it's going up and down the center. So this is the AC waveform. And if you want to have a DC component, you add in a DC component plus any value. For example, you want to have a value of 2. Okay, you will see that the sine wave will not be oscillating around the x-axis, but the whole waveform will be moved up and oscillating around the 2, y equals 2. All right, so this is, if I change this to another number, so it will go up and down, go and down. So this expression here, -3, is the DC component, and the one that is moving up and down is the AC component. All right, so I hope that I answered the question just now for the AC and the DC. So in all waveform, any waveform, it consists of like a DC and an AC component. So this is the expression to illustrate this. So another one is, let me clear this one. And let me show you the expression for a non-sinusoidal waveform. Example, you want to type in the expression of y equals sine. You can type in the sine, or you can actually use a function here for you to plug in, let's say for trigonometry, you can put in sine here, or you can type in and it will come up by itself. Sine t, okay, plus 1/3 sine 3t plus 1/5 sine 5t plus 1/7 sine 7t plus 1/9 sine 9t. So you can see the more terms I add here, the more and more it becomes like a square wave. Okay, so this expression tells you that not a square wave actually consists of many sine waves combined together to get this waveform. All right. So, but writing all these expression is taking a lot of time, and also you don't want to continue after the 1, 2, 3, 4, 5 term. You get tired. So what you do is that you can actually put the expression of the summation. So let me to not display. If you don't want to display this graph here, you just click this box here. You click the box here, and then the graph will not appear. So you can create another graph here. Let's say this is y equals. Then you need to go into this function here. The function will open up, and you go into miscellaneous, and you go into this expression called the this is the summation. Okay, so over here you see the summation symbol will come up into your expression or your equation. You put in, let's say, the n equals to 0, and this one will be, let's say, you want to make it a variable, say m, and this one we want to put in as a sine, okay, open bracket, 2n plus 1t close bracket, and then divide everything with 2n plus 1 and close bracket, and you put in the slider for m. So you can see if I auto zoom the scale here. Okay, so this is okay, I think I got something wrong here. To sine open bracket sine 2n plus 1. Okay, I forgot to close one bracket here. To n plus 1t, 2n plus 1. All right, so and the m I need to change because m need to be an integer. The m is, so what this equation is saying is change your n from 0, 1, 2, 3, 4, 5 until m. So we need to define m here. Since m need to be an integer, you will change the range. If you click on the lower range here, say that you start from a 0, and then the range here you actually put in a factor of, let's say, okay, 20. A step means that you want how many steps you want to actually go through at one time. So let's say we have a one step at a time. So this is the expression, and when you actually animate it, okay, I think there's something not right here. Okay, let me go back to this equation here. M is 9. Give me a minute, fine. Okay. Open bracket. 2n plus 1. Close bracket. And then you have a t expression. Then divide by 2n plus 1. Okay, here you go. Just now I didn't time it properly. So this is the square wave. If I change my parameter here 9 to an M, and I can add a slider of a M. So my slider can change from 0 to maybe 20 and a step size of, let's say, 1. So you can see that if I slide my slider to 0, it's a sine wave. Okay. If I put my slider to maybe 1, 2, 3, 4, and you can see that it is more and more like a square wave. All right. So now the thing is, this is how you write the equation in simplified form. Rather than putting all this into a long expression, you can actually write the expression as the summation form. And from here, you can also automate. You automate this, you can see it changes from a sine wave and forming slowly into a square wave. Okay, okay, so you actually change the different speed of it, and it can become faster or slow, up to you. Okay, so from here you can actually try it out yourself. So in the exercise, there is the sawtooth and the triangle wave that you have to try it out yourself, and type in the equation and then see for yourself the equation, the expression into the waveform. Okay, so I think this is the end of my demo. So at this moment, I think there's a question. If you have a set of data in a table form, can we use this Desmos application? Okay, there is. Okay, you can actually plug in your data into a table form, and you can actually plot the data into the equation. Yes, you can. But I've not used it, but it's available. Can you, maybe you can actually go into Desmos and look into the examples. Like for example, you can see under help, under the help, you will see a lot of like, let's say tables, under tables. Okay, let's make a table over here. Table, under there you can add your table, and then after that, let's say this is 0. Okay, this is my first time doing this. And this is the 2, and then this is the 5, and this is the 6, and this is the 9, and this is the 11, and this is maybe 20 or 20. Okay, so if I display this off, take out this display. Oh, I see. Okay, it plots for you. Yes, it does plot for you. There you go. So with the table, you will plot for you on the graph also. All right. Okay. So this is the end of my session for this time. It's already 2 hours, 12 o'clock already. Any questions so far? So if you have any question, you just go to the Google Classroom and then post your question, and I will answer them one by one.
Okay, all the teachers, please don't left this webinar first, because you guys need to scan one more QR code for JPN Pulau Pinang. Okay, so let me share my screen first. So before that, maybe some of you want to see the Google Classroom code. Maybe Diana, can you share again the Google Classroom? Okay, so before we end, I would like for the teachers to go to the Google Classroom and then prepare for the next week. Please go to Matisim Live first, and please sign up this one first. Sign up just for free, because we will learn the tools inside the Matisim. So it's more toward the oscilloscope simulation. Okay, so we will learn this thing next week. Okay, so before we end, so how to sign up? So go to Matisim, and then you need to click on sign up and then fill in the form and then click on the create account. Just print, no worries, don't need to pay.